Hi, chemistry students. Mrs. Carlin here. In this video, I'm going to accomplish three things with you, hopefully. I want to quickly summarize the three rules that you read about that describe how electrons arrange themselves around the nucleus in an atom. I'm going to teach you how to draw something called an Aufbau diagram. And then lastly, I'm going to teach you how to use your filled-in Aufbau diagram to write something called an electron configuration. Electron configurations are going to be very, very important in our coming units, so make sure that you are able to write them out. So we have learned kind of periodically throughout the course of the school year so far, everything in nature seeks stability. Electrons also follow that theme, that rule. So when electrons arrange themselves around the nucleus of an atom, they'll do so in the most stable way possible. Low energy is a stable configuration. So another way to say this is that electrons arrange themselves around the nucleus in the lowest energy configuration possible. And how they do this is by following the three rules that you read about: Hund's rule, the Aufbau principle, and the Pauli exclusion principle. Let's start with the Aufbau principle. So the Aufbau principle states that electrons occupy orbitals of lowest energy first. How are you supposed to know what is the lowest energy? Well, that's where looking at this Aufbau diagram is really, really helpful. So at the very bottom of this Aufbau diagram is low energy. And then as you go up, right, the energy increases. So what that tells us is that the 1s is much, much lower in energy than, say, the 3d. Okay. So if electrons start to fill into these orbitals, they're going to start at the 1s and then follow the energy increasing pattern that we see in this Aufbau diagram. The second rule that electrons follow when they arrange themselves around the nucleus is called the Pauli exclusion principle. What the Pauli exclusion principle states is that only 2 electrons may occupy an atomic orbital at any time, right? So in the 1s, for instance, we can only fit 2 electrons. It can have 1, right? But we can't have 3 or 4 or 5. We can only have 2. So when we draw them in as spin up and spin down. Okay. And we draw them with these kind of weird looking arrows that only have like half of the tip so that we can draw them next to each other more easily. That's really the only reason we do that. So when we have a spin up electron and a spin down electron in an atomic orbital, they're said to be spin paired. Now, are electrons really spinning in space, one spinning up, one spinning down? No, electrons don't physically spin. It's an intrinsic mathematical property that physicists just sort of assigned to electrons so that these 2 electrons in the 1s, they have the same energy, but they're in the same atomic orbital, they're in the same sublevel. So we have to be able to differentiate between the 2. And this is how physicists did that. We said, well, one's spinning up, one's spinning down. This will be important when we talk about the last quantum number. Okay, so Pauli exclusion principle, I can only fit 2 electrons in each atomic orbital, and they have to be spin paired. The last rule that you read about is called Hund's rule. I like to call Hund's rule like the school bus rule. So if you think about when you were a little kid and you were getting on the school bus, right, when kids get on single file, like the ultimate thing is to be able to get a seat by yourself. So kids wouldn't start pairing up in the seats on the school bus until every seat had 1 kid in it already. Electrons do the same thing. So electrons fill orbitals in an atomic orbital in a way to maximize the number of unpaired electrons. And then all electrons in a singly occupied orbital must have the same spin. So it's either spin up or spin down. So let me give you an example. So this is the 3D, and let's say I'm going to put 4 electrons in the 3D. When I do that, to draw it like this. 1, 2, 3, 4. So notice that it's not 2 here and 2 here. I'm trying to maximize the number of unpaired electrons. If I was going to have 6 electrons in this orbital, it would have to go like this, right? I would draw the 5th here, and then I can start doubling them up with the 6th, right? And then we spin pair them. So when we combine these 3 rules, it allows us to draw like Aufbau diagrams. So let's draw an Aufbau diagram for the element carbon. Okay, carbon has atomic number 6, so it is going to have 6 electrons that we're going to try and fit into these atomic orbitals. How are they arranged? Well, the Aufbau principle says that I have to start at the 1s. Okay, so 1, 2. I'm going to increase in energy, 3, 4, 5. Now I'm going to follow Hund's rule, and I'm not going to put my 6th electron in that 2px. It has to go over in the 2py, and it has to have the same spin orientation, 6. Okay, the Aufbau diagram tells you the order of increasing energy. Okay, so you'll notice, hopefully, that the 4s is lower in energy than the 3d. So make sure you follow the order of the Aufbau diagram. Let's do one other one. Let's kind of do maybe a bigger element. Let's maybe try chlorine. Chlorine is element number 17, so it has 17 electrons. Let's check it out. 1, 2, 3, 4. Even though I know I'm going to fill this, I'm still going to fill it following Hund's rule. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So that's the Aufbau diagram for chlorine. Now, using an Aufbau diagram, you can write something called an electron configuration, which is the same information in the Aufbau diagram, but you don't have to have all of these boxes, and it takes up a little bit less room. So what we do is we follow the Aufbau principle, and we start with the lowest energy, right? So 1, whoops, that's not where I want to write that. Here we go. 1s, and there are 2 electrons in the 1s. Then 2s, there are 2 electrons in there. The 3, not the 3, excuse me. The 2p, right, we write all of the p's together, so it's just 2p. There are 6 in the 2p. In the 3s, there are 2. And in the 3p, there are 5. Okay, so that's the electron configuration for chlorine. In this unit, you'll have to draw Aufbau diagrams first before you can write electron configurations. When we learn a little bit better about the organization of the periodic table, you'll be able to write these electron configurations without having to draw Aufbau diagrams. All right, so this leads me to something that's going to tie up a loose end. You might remember that we learned about the principal quantum number and the angular momentum quantum number. These are the last 2 quantum numbers. The magnetic quantum number says which orientation in 3D space the atomic orbital, the electron occupies. And the spin quantum number is whether it is spin up or spin down. Take a shot at that Aufbau diagram homework, and we will go over it in class. Thank you. Good luck.